For 5.2, we're going to talk about exponential functions. This is of the form f of x or y equals some number raised to x in the exponent. Okay. Now, if this a is greater than 1, we call it exponential growth. And if this a is between 0 and 1, we call it exponential decay. And we'll see these two examples right here. So 2 to the x, and you've seen these in science class and algebra 2 as well, but anyway, let's start by making a table and plotting the points. Okay, so any number to the 0 power is 1. To the first, 2 to the first is 2. 2 squared, 2 times 2 is 4. 2 times 2 times 2 is 8. Okay, to the negative 1, remember negative exponents, we move it to the bottom, so we get 1/2. 2 to the negative 2, move it to the bottom, to be 1/4, and etc. 1/8. Okay, now if we plot these points here, okay, 0, 1, 1, 2, 3, 4, and then 8, okay, and then 1/2, 1/4, 1/8. Okay, so we get like this. Okay, so this is called exponential growth. Okay, our domain goes all the way this way and all the way this way, right? We can put any number in there for that x. It can be, positive or negative. So our domain is all real numbers. And our range, okay, now if I keep taking, notice going this direction, I always keep taking half. If I keep taking half of a number, will I ever reach 0? Nope. So we know that our y's are going to be greater than or 0, not equal to 0. We have that asymptote there at 0. Okay, so it's going to be greater. So there's a horizontal asymptote at y equals 0. Okay, for decay, sort of the same thing, except that this is between 0 and 1, like 1/2 is between 0 and 1. So if I take 1/2 to the 0 power, anything to the 0 power is 1. Notice that, anything to the 0 power is 1, right? Okay, and then 1/2, if I square this, it'd be 1/4, and 1/8. To the negative power switches it around, so 2, and then 4, and then 2 to the third is 8. Okay, notice it just kind of flipped around, isn't it? Okay, so we have 0, 1, 1 and 1/2, 1/4, 1/8, negative 1 and 2, and 4 and 8. Okay, so we have a graph that goes like this. So with growth, as I increase, it's growing, and y, as my x's increase, it's decaying. Okay, once again, my domain is all real numbers, this way and that way. It'll keep going both directions. The range, once again, I have an asymptote here at 0, so y has to be greater than 0. And then my horizontal asymptote is at y equals 0. Okay, so those are our basic parent functions. And then we're going to look at the transformations. Okay, so what if I have a negative here, a negative 2? Okay, so the negative, remember, with x squared, instead of opening it up, it opened down. Same idea here. So if my parent function 2 to the x looks like this, right? You can see the reflection of that would be like this. So instead of going through 1, it goes through a negative 1 there. Okay, so that's what the reflection looks like. Okay, plus 3. If we think about this plus 3, just like, for example, if I had x plus 3 squared, right? Remember how that moved right and left? Same idea here, it moves right and left. So it's going to move negative 3. So if you think about this point, usually goes through 1 right here, right? Shifts to the left. If it's plus 3 here, okay, thinking about the original graph, okay, 2 to the x goes through at 1 there, right? So it'll go up 3, 4, right? So it's going to shift here. Now my asymptote is no longer at 0, but it's at 3. Okay, so it shifts our asymptote up there as well. Okay, so what does this one do? Compared to my original graph, just 2 looks like this, right? So it's going to shift down 3, So now my asymptote is down here, right? Instead of at 0, it's down here at -3. So our asymptote is at y is equal to -3. And it's all shifting left 1. So this, I always like to use the point 1. It goes 1, 2, 3, and over this way 1 of your graph. Okay, so that's the transitions there. Okay, it says here to use the graph of 2 to the x to evaluate this, 2 to the square root of 6. Yeah, not real important here, but the square root of 6 is 2 point whatever there. And if we go to our graph, if I go to 2 to the x, right? So 2 point whatever, you could estimate it from the graph there. It'd be around, I don't know, 5.5 or something. Okay, but you can also use your calculator, and you just put in your calculator as well. It'd be 5.46. Okay, negative square root of 2. Square root of 2 is 1.41. Okay, so negative 2 point. So if we go to this, negative 1.4 something, you can see it's right there. You could also use your calculator to evaluate, and it would be about 2.67. Oh, I'm sorry, I looked at the wrong graph up there. This is 1/2 to that power, so I'm using this one, right? So negative 1 point something there, you can see it's right there. Around 2.67. Okay, so that's a little bit about the graphs. Let's actually solve them. We're going to do them both analytically and graphically here. To solve them analytically, we want to try and get the same bases to these. So for example, 25 is the same thing as 5 squared. Okay, so I could say this is 5 to the 2x right here. On the other side, this is 5 times 5 times 5 would be 5 to the 3rd. So now that I have the same bases, I can say that 2x is equal to 3. So x is equal to 3 over 2. And you can take that and plug it back in and make sure it does work that. Actually, you could do this as well. Remember 25 to the 3 over 2. Remember that's the square root of 25 to the 3rd, right? Square root of 25 is 5. 5 times 3 is, to the 3rd power is 125. Okay, so let's check. We're good. Okay. The next one here, get these to the same bases. I'm going to try and get them to be 3. You could get them both to be 1/3 as well, but I'm going to get it to be 3. So this would be 3 to the negative 1 is 1/3, right? Okay, so remember how it's negative moves to the bottom, right? So this would be 3 to the negative x. And this would be 81 is the same as 3 times 3 times 3 times 3 is 3 to the 4th. So now that I have the same bases, I can say that negative x is equal to 4, therefore x equals negative 4. Once again, you could take it and plug it in there and make sure it works. Okay, with this one, this would be 3 over 2 to the x plus 1. Okay, so I notice that this, if we take this cubed and this cubed, right? So if I take 3 over 2 cubed, that's 27 over 8. Okay, so now I have the same bases, so I can say that x plus 1 is equal to 3x. And I can subtract that over and divide, I get x is 1/2. Okay, now to do this using a calculator, using a graphical approach, what I would do is this. I would take 25x minus 125 and I would graph this. And let me get a graph for this. Okay, and if I graph this, I don't know exactly what it looks like, but it looks there's a line going through like this. I'm not sure what happens up there and there, but I know that it intercepts at 0 at that. Okay, and if I take this one, 1/3 to the x minus 81, and I graph this, I'll get a line here at negative 4. And if I take 1.5 to the x plus 1 minus 28 over 27 over 8 to the x, and if I graph this, it goes through at 1/2. Right, so it actually kind of goes like this, but it goes through at 1/2. Okay? So now, with inequalities, I want you to just look at the graphs. So once again, you want to get this equal to 0. So take your 1.5 to the x plus 1 minus 27/8 raised to the x. Okay, so you want to graph this, and we kind of have the graph from before up here, right? So the graph looks something like this. Okay. I actually just put this into Desmos. Make sure in Desmos it's a little tricky. You want to put this in parentheses. When putting this in parentheses there, when you or else it won't let you put two things in the exponent. Okay, but anyway, here's your graph. So where is it greater than 0? It's greater than 0 from negative infinity up through 1/2. And where is it less than 0? Okay, less than 0 would be from 1/2 through infinity. Okay, so now we're going to apply these exponents a little bit. One of the ways is with interest. So a simple interest sort of thing is interest is equal to principal times rate times time. That's just kind of a simple interest thing. But more specifically, you monthly, usually if you have money in a bank account, monthly you get interest earned. Okay, so this is the equation they use for that. So principal, A is the amount out at the end. P is the amount you start with. And R is your rate, is a percentage rate that you earned. N is the number of times compounded. And T is the time. Okay, so say we have $1,000 invested in an annual rate of 4%, compounded quarterly, so 4 times a year. You get quarterly is 4 times per year. How much will it be an account after 10 years? Okay, so our amount at the end will equal our principal, which we put in $1,000, and our rate was 4%, so 0.04, and compounded quarterly, so quarterly would be 4 times per year, and we're putting it in for 10 years. Okay, so you want to work that out and find what your answer is. Okay, I just put that in the calculator, and I have 1488.86. Okay, so you'd have that one. So you earned $488, almost $89 on interest in those 10 years. Okay, so let's talk about stocks a little bit. Okay, the stock market. These are average returns. The S&P 500 is your largest 500 companies in the U.S. And since 1951, I think I wrote there. 1957, should be 1957. I'm not sure what that other little thing is there. Anyway, since 1957 is when they tracked it. If you put something in there, you would have gained till present. I just looked this up the other day. About 8% per year. Okay, in the last 10 years, the S&P has gone up 14.7%. In the last 20 years, 5.9%. In the last 30 years, 10.99%. This includes those really bad years where we had the big depression went down right after 9/11. Okay, but anyway, these are kind of the average returns. So let's say you were born in the year 2000, which I think some of you might have been. Your grandma put $500 into a index fund, okay, S&P index fund. How much is in the fund in 2020 if compounded monthly? Okay, so that'd be 20 years. Okay, so how much is in the fund if your grandma put in $500 for you, and the rate was 5.9%? which is kind of what they say. They say average, 5-6%, something like that, if you put it in there. Compounded monthly, so that's 12 times per year for 20 years. Okay, so if we work that out, I'm going to pause it and work it out. Okay, so that $500 turns into $1,622.49 if it continues to run. Okay, so stock market keeps going up and down, whatever. But if you think about the graph of these, okay, you started with 500. In the beginning, the first couple years, this is our time, this is the amount of money in the account, it doesn't grow a whole lot, okay? But over time, it grows exponentially because you're earning interest upon the interest that you've earned before. So we have this exponential growth. So as you get out to 20, 25, 30 years, it really, really grows, okay? So if you have money, you don't know what to do with it, if you can invest it in something that earns a higher interest rate. Stocks are kind of high right now. They've actually the highest they've ever been right now. So might not be the best time to put in the stocks. I don't know. So you can make that the choice though. But yeah, stocks go up and down, up and down, up and down a lot. But over time, they rise exponentially and average that amount. Okay. So another thing, compounded continuously. Now this doesn't happen too much in the real world, but the more you compound it, the more interest you earn. So if I compounded it once a year versus quarterly, 4 times a year versus monthly versus daily even. Like for example, if I put this into this equation, if I put 365, I'll put it in the calculator here real quick. If we did it daily, wouldn't be a whole lot more, but it would be a little bit more. Okay, so the more that we compound it, the more interest there is. The interest rate has a huge impact, and how much you start with also has a big impact. Okay, so a little bit of that. But if we continually compound it, we use this equation. Okay, the more often, yeah. So we talked about the amount is equal to 1 divided by 1 over k raised to the k. K is how much is compounded, but it keeps increasing. The value keeps getting closer and closer to a fixed number, which is e. Okay, this is their number e. So just like pi is irrational, 3.1415, right? Blah, 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 e is also this irrational number. Okay, it's another kind of famously irrational number, math famous. So this is, if it's compounded continually, it's our principal times e raised to the RT. Okay, so suppose we have $500. So we have $500 compounded continuous. We're going to use this e at a rate of 3%, so not as high percentage rise, and compounded continually for 5 years. Okay, I'm going to put this in Desmos. I'm not sure where the e is there, but I think you can just type the e. Yeah, so you can just in Desmos just type e in, the letter e, and it'll read it as that number. Okay, so 500 e to the 0.03 times 5 gives you $580.92. Okay. Okay, you can also apply this to other scenarios besides money. So the chance of dying of influenza, flu, or pneumonia increases exponentially after the age of 55. So before the age of 55, probably pretty low, but after 55 and you get up into 70s and 80s and so forth, you have a higher percentage of chance of dying. Okay, it rises exponentially. So according to this function, R is sort of our risk factor. So at 55, if you're higher risk versus lower risk, that's kind of our beginning point with this. Okay, and this is X is the number of years greater than 55. So we want to compare the risk at age 75 to the risk at age 55. Okay, so basically I want to find f of 20 because there's a 20-year difference between the two, right? So if I find this, if I work this out, this comes up to be 4.84R. So whatever our risk factor is, 55 versus 75, 75-year-olds have a 4.89 higher chance of dying. Okay, almost 5 times greater. Okay, so we can also apply it to others. Basically any data that rises exponentially, we can use the exponential stuff for.